Welcome to the lecture on viewing, which is a part of the course on computer graphics at KAUST. Today, we will be talking about how do we realize the viewing, namely how do we make an image of a particular scene, given that the camera is placed somewhere within this scene. We will be talking about how do we map the 3D world coordinates of objects into the 2D coordinates of the screen in terms of pixel coordinates. We have several different types of viewing possibilities, such as, for example, an orthographic projection or a perspective projection, and we will be dealing with this and explaining how to realize them in a mathematical framework that allows them to transform the coordinates accordingly. So we start with a known scene. For the purpose of this lecture, the scene will be consisting of points, which are then connected into edges, which then can form higher level objects, such as triangles, and these triangles can form a triangle mesh. So this viewing transformation description relates to scenes which are defined by such points, and we will be transforming these points. These points are originally in associated with a certain object, and this object is defined in the local coordinate system of a certain object. And then first we will be taking this object and putting it into the scene, and by that the points of these objects which are put into the scene will get their world coordinates. So each point will have the world coordinates x, y, z at the beginning, and the transformation which brings them into the world coordinates is essentially the modeling transformation. And from then on, we will be applying the viewing transformation to map them onto the pixel coordinates. So first, we decompose this complex transformation problem into several smaller tractable transformations. And these transformations will be the camera transformation, meaning that we, instead of world coordinates, we will be representing the points in so-called eye space or camera space. So we will be going from world coordinate system to a camera coordinate system, which effectively places the camera at the origin, and it's oriented so that it is looking into the negative z direction. Afterwards, after we have done this, we perform the so-called projection transformation, and first we map our objects, which are to be viewed eventually on the screen, into a space which is kind of a normalized space between the values -1 and 1. So everything will be scaled down to a -1, 1 cubed box. Finally, we will be using the so-called viewpoint transformation, which takes the coordinates in which are these normalized the coordinates, and scales them onto the window resolution, onto the coordinates of the viewpoint. Sorry, here is a mistake. It is not viewpoint, but viewport. We are not talking about one point, but actually on the screen which this viewport represents. We will start with going through these transformations and explaining those. However, we will start in somehow backwards order. So first, we will be talking about the uh, transformation between the normalized coordinates into the pixel coordinates. So this viewport transformation we will describe the first. But before doing that, we will explain once again the viewing transformation logic. As I said, first we have all our objects and their corresponding points um, structured in some local coordinate system of that particular object. The zero origin for that coordinate space might be, for example, centered in the center of the object. Then we are placing these objects into the scene and we are assigning them the world coordinates, and also our camera will be assigned some world coordinates. So it will not be in some kind of a nice location, but it will be an arbitrary location. Now, our object is this R, and we, as you can see, we have placed it into the scene. Now, the world coordinates for the viewing are not so useful. Therefore, we will change the coordinates of our object depicted by this letter R into the camera coordinates. So we will transform all its points into the camera space. This camera space is often referred to an I space. And you can see that now the origin of this coordinate space is is where the camera is. So the 0, 0, 0 is at the camera position, and the camera will be looking into the negative z direction. We will come to that later. And then we will be normalizing this I space so that the space which we are, the view volume which we are looking at, will be then squeezed, scaled into the normalized device coordinates, or the so-called canonical view volume. And from that, we will simply map the normalized device coordinates to the pixel coordinates. And we will start with that right away. So the so-called viewport transformation, not viewpoint, as it was wrongly written on the slide, starts with having all our points being already transformed into the -1, 1 cubed. So although in the book and here we have here some coordinates L, B, N, and RTF. These actually are corresponding to the view volume from the camera space. And so this was incorrectly described in the book, and we want to have here at this point in the canonical view volume -1, -1, -1 at this position, and at this position we would like to have the 1, 1, 1. Okay, so the x, y, and z values will be then within the range -1, 1, as shown here. And now we would like to map them onto the screen coordinates. The screen is defined by a certain resolution. So we have the resolution of the screen is an x and y. And now we would like to essentially map the x and y coordinates into the x and y coordinates into the range 0 to nx and 0 to ny. But actually we want the -1, the very border, to be on -0.5. You remember the pixel center would be starting at 0, but its associated area will be going to the value -0.5 minus 0.5. So therefore, -1 is mapped to -0.5, and 1 is mapped to nx minus 0.5. And similarly, this also holds for the ny, and where we map the y coordinate to -0.5 and ny minus 0.5. So imagine that our normalized coordinates are now within the range -1, 1, and the length of this interval is 2. So what we would like to do is to scale first, because let's say nx equals 640 and ny equals 480, which is the VGA resolution from many years back. And now we want to scale it up, this -1, 1 range. So by how much do we want to scale it up? We want to scale it up from the range -1, 1 to -0.5 to 640 minus -0.5. So we first scale it by the factor nx divided by 2, which will be 320 in our particular case. So, for example, the point -1 will be scaled, and the x-coordinate will be scaled to 320. That's first the scaling, so it will be minus 320. And then we will, you see, so this is the scaling matrix, and this is the translational matrix. So we will be now moving this point -320 to 320 minus 1 divided by 2. Oh, sorry, 640 minus 1 divided by 2. So let's just calculate it. 640 divided by 2 xc plus 640 minus 1 divided by 2. So, and the xc is now, we put -1 there so that we have some particular value to deal with. So this is 600, let's put this under one fraction. So we have 2 here, and we have here minus 640 plus 640 minus 1. And this is 640 minus 640, 0. So we have -1/2. So we have managed to put with this viewport transformation matrix, this is a two-dimensional plus homogeneous coordinate transformation matrix, we have managed to put our transformation matrix, the -1 to -0.5. Now, should we try for the upper end? Maybe we can try that too. So if we have our upper end, which is 1, so we have 320, or let's say 640, so that we keep it on our fraction. 640 divided by 2 times 1 plus, and now 640 minus 1 divided by 2. So this is now 640 plus 640 minus 1 divided by 2. and this equals to 1280 minus 1 divided by 2. And you can see what we want to achieve is nx minus 0.5. So this is equal to 640 minus 0.5, which is 1/2 in this case. So yes, also the other end of this interval will be correctly mapped. And as this is a affine transformation, we will have a smooth transition between -1 mapped to minus 0.5 to nx minus 0.5. And the same will hold for the y dimension. So here is the viewport transformation matrix as we can see it, but for three-dimensional case. We can see here that the z value is not really transformed. It is just passed on and also not translated. So our z value will stay in the same coordinates as it was in the previous stage, meaning that it will stay in these normalized device coordinates, which were given at the input. Now let's work out the viewing transformation backwards. We have now managed to perform the last stage of the viewing transformation, namely to move our points transform our points from the normalized device coordinates, from this canonical view volume -1, 1 cubed, into the coordinates of the screen, especially the x and y coordinates, while the z coordinate was unchanged. Now we need to get in the next step backwards going. We need to get our points into the normalized device coordinates, into this canonical view volume. And after the camera transformation, we will have our points in the camera space. And there we will define what we want to, from the scene, actually map onto the screen, because not the entire screen necessarily needs to be shown, only a certain view volume. And we define this view volume by 6 planes, defining as the left, right, bottom, top, near, and far planes, which constitute this view volume, which partition the space so that we create this box which is marked as border by these planes. There is one thing to remember. We will be dealing with the right-handed coordinate system. And in this right-handed coordinate system, we find it very attractive that our x coordinate is the horizontal coordinate going from left to right, and our y coordinate is the vertical coordinate going from bottom to top. But as we have the right-handed coordinate system, then the z direction has to go away from our viewing direction, and therefore we will be looking from the origin into the negative coordinate of the z direction. So the near plane will be having actually a higher value than the far plane. In absolute values, the near plane will be smaller than the far plane, but they are negative values, so the number for defining the near plane will be higher number along the real axis of numbers than the far plane. Therefore, you can see here that we have far near, so always our interval starts from the smaller number towards the bigger number. So this is a slight inconsistency which is caused by the right-handed coordinate system which we are using. So we have now an orthographic projection where we need to project our points, which are having the coordinates within these boundaries of these planes, into the um, interval 1 minus 1 1 cubed. So basically what we want to do is to, so that we can perform this scaling, what we want to do is to take this center of this cube, move it to the origin, and then scale it so that this length will be then eventually, or let's say this length and this length, all of them will be of length 2, between minus 1, 1. So we will therefore move this point first to the origin and then perform the scaling. So here it is the two transformations which we are doing. You see that this point, its coordinates in the x coordinates are in the middle between left and right, and so left plus right coordinate divided by 2. So it's an average value of these two coordinates in the x dimension. And now, as we are in the uh, we want this coordinate, the x coordinate, which we calculated, we want to move to 0, 0. So we make a negative translation. So it brings us this point to the coordinate origin. And in the second step, we will be performing the scaling. Now, imagine that the scaling should be somehow shrinking in case our range between L and R is, let's say, minus 100 to 100. Then we perform the scaling should be somehow making it so small that it fits into minus 1, 1. So the scaling factor here would be 100. How can we do it? We can see it here that we can achieve a scaling factor of 100. In this case, if we have here minus 1, 1 is the length of the interval is 2, and minus 100 to 100, the length of the interval is 200. So 2 divided by 200 will be, for this particular case, 0.01 will be the scaling factor, which is exactly what we will have for the x. And perhaps we will have similar values for the y and for the z. So you can see how the scaling factors are now scaling our box into this normalized device coordinates. So after this performing these two transformations, we will have our view volume into this canonical view volume transformed so that all the coordinates will be now scaled into the range minus 1, 1, so that we can perform the viewport transformation, which we have already discussed. Here is our orthographic projection transformation matrix, where we have the translation factors and the scaling factors. Now, this is a 4 by 4 matrix, which we can see here with the homogeneous coordinates here. And what we can recognize here is that we have the scaling matrix here. The scaling matrix is here, defining us the scaling factors as we just discussed them along the diagonal, so that everything seems to be all right. And here we can see that we have the translational factors. But the translational factors do not look like the translational factors which we had before. Why is that? Remember, if we have a matrix which has homogeneous coordinates, and let's say for the sake of explanation, we will have an 2 by 2 two-dimensional case. So we have 2 by 2 matrix for which is responsible for rotation, for scaling, for reflection, then we will have the homogeneous coordinates part here, where we will have the number 1, and then we will have the translational part here. The translational part, as we know from these types of matrix, will be applied after the, so this will be the first transformation, and the translation will be the second transformation. Then, if that's the case, then we will see here the translation factors as we would expect. However, if the translation and let's say rotation, or let's say scaling, so that it's identical to our case, scaling. So if we first do the translation and then we do the scaling, as is the case in our case, because we move the viewing volume first into the origin and then scale, then we cannot expect that here in the last column we will recognize the translation factors. They have been already scaled with our scaling factors through this multiplication. That's why they look a little bit different. If you want to calculate the factors once again, you can simply take the two matrices. So this will be the translational matrix, which is 1, 0, 0, and this will be minus R plus L divided by 2, and 0, 1, 0 minus D plus B divided by 2, and 0, 0, 1. Sorry, I need to create here space for the homogeneous coordinates as well. And this will be minus N plus F divided by 2, 0, 0, 0, 1. And here we will have the scaling matrix, which is the 2 divided by R minus L, 0, 0, 0, and 0, 2, T minus B, 0, 0, and 0, 0, 2 divided by N minus F, 0, and 0, 0, 0, 1. If we will multiply these two transformations, scaling and translation, we can see how this R minus L will leak into the denominator, and the 2's will be taken out from the fraction because they appear in the denominator and in the numerator as well. So this is our final matrix for the three-dimensional projection transformation, which is orthographic one. Orthographic means that we do not have any perspective there. It is just preserving the same orientation, for example, of lines. If the lines will be parallel to each other in the camera space, they will remain parallel to each other also after this orthographic projection transformation. The next step is, or better to say, the first step in our viewing transformation will be the camera transformation, which will bring our world coordinates into the camera space, camera coordinates, so that our camera will be at the origin of this coordinate space, and the coordinates of this space will be oriented in such a way that we will be looking straight into the negative z direction of this camera space. So and then we will follow with the other transformations, like the projection transformation and then the viewport transformation, which we already have discussed before. So camera is typically defined by some intuitive parameters such as the point in the 3D world where the camera is placed, the orientation in the which direction it is looking, so the gaze direction, and the scene typically would have some logical up vector which will define what is up and what is down so that the camera can be oriented in the correct way, where the top of the camera will be pointing towards the top. Not exactly to the top, but in principle, that direction. So if we have these defined properties of the scene and the camera, we will create the coordinate system which will define the camera coordinate system and into which we will transform all the world coordinate points into this camera coordinate system positions. So, and this is realized, the coordinate system generation, through this typical trick where we know one vector, which will be the gaze vector, and we will normalize this gaze vector, and this will serve us as one axis of this coordinate system. However, keep in mind that we are dealing with the right-handed coordinate system, where if we will have the convenience of the x-axis pointing towards the right side and from the left and y-axis going from bottom to top, then the z-axis has to be pointing towards us. That's the right-handed coordinate system. Therefore, the z negative z will be actually the gaze direction. So this, therefore, we construct the coordinate system with the basis vectors defining as the w first will be the negative g and unit vector. Out of that, through the top vector and the generated w vector, we will generate through cross product and normalization another vector, the u vector, which will be perpendicular to both top vector and the w vector. And from this u vector, we will define the v vector as a cross product between the two orthogonal and unit vectors w and u. So this way, we will generate first our camera coordinate system UVW. Once we have that, we can put we can realize where is this coordinate system, and through these coordinate system transformations which we had before, we can map the the world coordinates into these camera coordinates, so that the camera coordinates will then be from the point E, which will be the origin of our camera coordinate system. And later on, you can already see, once we have this, we will refer the view volume defined by the planes L, R, T, B, N, and F will be already defined in this camera space using the camera coordinate system. So let's get transformed the points from the world space to the camera space, or to the eye space, as it's sometimes called. What do we need to do for that? Well, first, this is a simple operation of the transformation which we already had at the end of the last lecture on matrix transformations. You remember there we first had a transformation which was transforming our points into the canonical coordinate system points, and the second transformation was the transformation which was the inverse to it, transforming the canonical coordinates into the UVW coordinates. And this is what we will do in this case. We are transforming the UVW coordinates we are transforming the XYZ coordinates into the UVW coordinates. And first, we will move our point E, translate it so that it is at the origin of the world coordinate system. And then we have our two coordinate systems placed on the same origin. However, the one is misoriented with respect to the other one. And for that, we are using the UVW, the rotational matrix, which rotates us the coordinate system UVW so that it is aligned with the XYZ coordinate system. So here you can see that this is the rotational matrix and it is inverse of that. And it is also then, as it is inverse of that, then it is also the transpose of the rotational matrix. So this would be the without inverse, this would be the matrix which brings us from the canonical coordinate system into the, from the UVW coordinate system into the canonical coordinate system, and the inverse of it goes the other direction. All right, so then we will have the camera transformation, which goal was to bring the world space coordinates of points into the camera space coordinates. And that's what we have done with this simple set of two transformations as we learned it on the previous lecture. So this is the matrix which is called the camera transformation matrix. And you remember we have had three transformations that form as the viewing transformation. So we have learned just recently, just now, about the camera transformation. Then we have the orthographic projection matrix and the viewport transformation matrix, which at the end we will get the screen coordinates of the X, Y, and Z. So at the input we have the world coordinates, and here we will have the screen coordinates. And in between we will have the camera space coordinates, then we will have the coordinates which are within this view volume, and finally we will have, which are then placed into the center of our coordinate system and scaled into the normalized coordinates, and those are then rescaled into the screen coordinates finally. So this is our viewing pipeline. Besides that, one thing we have omitted. We have not only orthographic projections, but we also can, in computer graphics, often have the perspective projections. And for those, we have so far not defined the framework, how this matrix will look like if the perspective transformation should be supported. So all that we have discussed so far relates to viewing transformation of the orthographic projection. And with that, we are done. This is already completed. And let's see now, how can we extend this already pipeline which we have created to support the perspective projection. So now, let's now have a little bit look at geometry. If we have a setting where we have two triangles, now let's have a look at the triangles first. So this would be a big triangle, and there will be another, I will use another color for that, there will be another triangle here. These two triangles are similar to each other. And now let's get back from the triangles to the scene. What we see here is an eye point here, and we see some point in the scene which is characterized. Now we do not have its x coordinate, but we have its y coordinate and we have its z coordinate. So in the world coordinates, actually in the eye space or camera space coordinates, it is its coordinates are y, z. Now, if we have a viewing plane placed here, then this point will project at the viewing plane somewhere by connecting the eye point or as a starting point of the perspective projection with the point itself in the coordinates of the camera space. And then we will see a projection of this perspective projection of this point on a viewing plane. Now let's go back to our discussion of the similar triangles. So we can see that there is a triangle defined by ZYE, and then there is a triangle defined by D distance from E to the viewing plane, then the projection coordinate of the Y, the YS, and then the E again. So the question is now, what is YS? And we can see that the similarity of the triangles give us the following relation. Y divided by Z is equal to YS divided by D. So from that, putting the D on the other side, we will end up with this equation. This is the equation where we see the position, the Y position of this projected point on the viewing plane. So it turns out that just reciprocal of Z is the right scaling factor of the Y coordinates in the I space in order to perform the perspective projection onto the plane which is far away from the eye point by the distance d. So that is the scaling factor which also plays a role in this perspective projection. So far with our system of matrices, we were able to deal with the following types of problems. For example, we were able to compute some coordinate as a linear combination of the coordinates of in all other dimensions, including the same dimension, by some factors a, b, and c. So these were the linear transformations. Then we extended through the homogeneous coordinates by having the last row just by 0, 0, and 1, or 0, 0, 0, and 1 of the matrix, and the last element of the column vector being 1 for the points and 0 for the vectors or directions. We were able to support the translation as well. Now, we have a look at this matrix again, and we can realize that the 0, 0, 0, 1 row of the three-dimensional transformation, affine transformation matrix, can be actually filled with some values, and by that we can realize a division which was not possible to realize before. So this division will be realized in such a way that we will accumulate the division factor in the last coordinate of our x, y, z, w vector. So this is the divider. And then finally, we will divide with this value all coordinates so that we will end up here with 1, and the other coordinates will be scaled by this vector. So we can, by that, expand our functionality of matrix arithmetics by this powerful division where these other vectors E, F, G, and H can be used to perform certain operations. For the sake of the perspective projection, this particular aspect will be very important for us. So here we can see the new matrix, if you like, where we have our rotation and shear and scaling and reflection in one part of the matrix. Here we have the consecutive translation of that encoded in that matrix, and here we have the dividers, which can be scaled by the coordinate values of our input vector. Here, please note that we have still this homogeneous coordinate equal to 1 on the input, but on the output, it can be an arbitrary value w with which we can scale, so that if it will be the entire vector will be scaled and the w will have the value 1, we will have the division by this w value here. So these are called the projective transformations, and we can understand them in the following geometric way. Let's assume that we have a value in homogeneous coordinates in sort of one-dimensional value of x is 1.5. In homogeneous coordinates, that will be 1.5 and 1. And through this machinery of homogeneous coordinates, this point, we will say that it's equivalent to a point 3, 2. So this point is equivalent to this point, but also this point, and also this point. So all these points on this line are equivalent, and they are just a multiplication of each other, and our sort of reference point of this one line will be the point 1.5 with the homogeneous coordinate 1. So always after, if we want to get the values of the coordinates of the homogeneous coordinates, at the end of the entire process, we will simply be scaling the entire vector by the last value, by the w value in the 3 dimensions. So we can also understand it as somehow rays which are emanating in the 2-dimensional case. So this was 1-dimensional case here. In the 2-dimensional case here, we can see that we have an xy plane, and the w is having a one plane which is w equals 0.1, and there our x and y points exist with the homogeneous coordinate 1, and there are other homogeneous coordinates which do not have the value 1, could have even a value 0, and this will correspond to slightly different coordinates of xy, which are, however, equivalent to some point on the plane w equals 1. So this is the notion of how we can use this w coordinate in 3 dimensions, or here in 2 dimensions in x, y, w system for the division, so that we obtain the values which are in the xy plane in the w equals to 1. And now let's perform a certain projective transformation. So here we have one example on the right hand side where we have a unit square with points 1, 0, this is point 0, 0, 1, 1, 0, and these points, and then point 0, 0, and point 1, 1, a unit square. And we are applying certain projective transformation, which for 2 dimensions will transform our points. The projective transformation has some values which are not equal to 1 as the last element here, and not equal to 0 to all to these elements before. So this realizes as the projection, so that there will be possible to create a division which will then correspond to some perspective projection or to a projective transformation. So we have here this 1.101. So the homogeneous coordinate is 1, but we are dealing with this point. So what will happen to this point? If we are now post-multiplying this point coordinates with the matrix, we will end up with a value 2 times 1 plus 0 times 0 plus minus 1 times 1 is 1. And then 0, 3, 0 times 1, 0, 1 will be 0. And then 0 times 1 is 0, 0 and 0 times 2 thirds is 0, and 1 times 1 third is 1 third. So this will correspond to a point which is 1, 0, 1 third. If we then divide by this coordinate to get the w value 1, this will be equivalent to a point 3, 0, 1. So the transformation with this matrix, the projective transformation, will map the point 1, 0 into point 3, 0. Let's just calculate the point 1, 1. What will happen to the point 1, 1? The point 1, 1 will have 2 times 1 plus 0 times 1 plus minus 1 times 1. So it will be again 1. Let's write it somewhere here. It's mapped to 1. And then in the x coordinates, and then for the y coordinate we will have 0 times 1, and then 3 times 1 will be there, and 0 times 1 third, so it will be 3 in the y coordinate. And for the homogeneous coordinate, we will have 0 times 1, 2 thirds times 1, plus 1 third times 1. So 2 thirds plus 1 third is 3 thirds, which is 1. So this one has already homogeneous coordinate equal to 1. So the coordinates of this point will turn out to be 3 in the y direction and 1 in the x direction. So we can see here this projective transformation of the unit square. Okay, so this will be a powerful machinery for our perspective projection. Let's come to this one-dimensional example, which we had from the previous slide. And we see that our point ys coordinate can be calculated through multiplication of these matrices. So d times y plus 0 times z plus 0 times 1 is dy here. So this will be equal, this multiplication will be equal to dy And then for the second row, it will be the 0 times y, 1 times z, and 0 times 1. So this will be z. And if this is now our homogeneous coordinate in this particular case, therefore it is equivalent to dy divided by z and 1 vector. And this is exactly what we want, because this is the ys as we have it on the left-hand side. So this way is how we can realize the perspective. We can simply divide by the z. And however, we need to scale by the values of the near plane in the following way. Our n is the near plane here, distance, the near plane coordinate, which is a negative value, but that is fine because we are looking into the negative z direction. So and n corresponds to the d distance here in this case. So we want to multiply by n as we are multiplying here by the d. And then because that defines as the distance on to which we are projecting our points based on and scaling their components, the x and y components. So this matrix looks complicated, but let's forget about the third row for a moment and let's consider the first, second, and fourth row, which are fairly simple. So what is going on here? In this perspective projection matrix, we are realizing we are first performing imagine that we have a certain x, y, z values. So I will x, y, z, and 1. And now what we will get as an output will be some vector which has so if we now multiply the row with the column, or row of the matrix with the column vector, we will have in the first result of this new vector, which is the result of this post multiplication, we will have an x, because the rest is zeros. For the y vector, we will have, for the y coordinate, we will have an y. So far, so good, because that's what we want to have, this multiplication with the distance from the coordinate origin. Then for the z, for the third, let's ignore that for the moment. And at the fourth component, we will have not 1 anymore, because we will have the 0 times x 0, 0 times y is 0, 1 times z is z, and 1 times 0 is 0. So we will have in the last coordinate z, and this will be our homogeneous coordinate with which we will be scaling the coordinates at the very end, and we will be by that be able to perform this perspective projection, this projection for shortening by the distance from the by the z coordinates in the I space. So let's have a look at the matrix again, and we can see here the result of our calculation of with some column vector x, y, z, and we can see what we already learned, and x and y and z. The divider is here, and then for the third element we have something mystical, and this is simply scaling the z value somehow on the way so that the z is has few properties that is not possible as we are using this z for the division. We need to we cannot really also maintain or preserve the z coordinate. What we can do is to at least have some function which will keep the z in the same order. So some z which were previously at in front of other z at the other distance, this will be preserved, but the distances will be a little bit non-linearly scaled along the way. And the nonlinear scaling will have another nice property, which will mean that if our z will be equal to the near plane distance, now we can see it here what will happen. So n plus f times z will be now equal to the n minus fn. So we will now have n plus f times n minus fn is equal to n uh, n, and if we have our z value, so for in case our distance will be equal to the far plane, then for this equation, what will be the value will be n plus f times f minus fn, which means that we will end up with the value ff here. But we will be, previously it was nn, now it is ff, but we will have always the corresponding homogeneous coordinate here, either n or f in these two cases, so we will be scaling by that eventually. So we will end up with the z coordinate, the n or f respectively for these two cases. If we are on the n plane, on the near plane, we will remain on the near plane, and if we will be on the far plane, our z will remain on the far plane. So that those z coordinates for these two distances will not be changed. Other interesting aspect is that in our viewing frustum, which we are creating by the values near plane and far plane and the projection transformation, which forms us this this pyramid stump. After the perspective projection applied, after this transformation, all our rays which are emanating from the eye point will become parallel to each other. So they were not parallel to each other before, and now they will become parallel to each other. So actually, we will get into this three-dimensional object, this pyramid stump, will be transformed into a box with where we can have our left, right, bottom, top, near and far planes. So, but the question is how to define the left and right in this case. Well, as we know, on the near plane, nothing is changing through this perspective transformation. Everything will remain as it is. There is no scaling of the x and y values, and the z value will remain the n on the near plane. Therefore, we can define these values L, R, T, and B for the near plane, and the near and far plane are also defining the rest of this after the perspective transformation applied box defined by these coordinates. So after this perspective projection, which we have used here, we will end up in some multiplication of our coordinates, and our homogeneous coordinate will not be equal to 0, but will be equal to z, because that will be the scaling factor later. It turns out that as we will end up with our perspective projection in a rectangular box, then we can simply use our orthographic projection afterwards and to simply put our points into the normalized device coordinates into this canonical view volume, which is this volume between -1, -1, -1, 1, 1, 1 points. So our perspective projection matrix will be a multiplication of the orthographic matrix with this perspective matrix, which we have just learned. So this is the perspective matrix, which with intuitive and first, second, and fourth row. The third row is this less intuitive scaling function, nonlinear scaling function of z, which has these properties that it keeps the end plane in the end plane, the far plane in the far plane, and scales the in between z values in such a way that it preserves the order. And this matrix is then multiplied with the orthographic projection matrix as we learned it, and multiplying these two will result into the perspective matrix as we can see it here. And we can recognize that some factors are there. We can obviously see that the n has made its way onto the diagonal of this matrix in the same way as the scaling of the orthographic projection matrix, and that our perspective division factor z is maintained there by this factor, and so on. So if we want to perform viewing transformation with the perspective projection, we can simply use the camera transformation as it was before, then the perspective projection matrix, and the viewport transformation matrix, which completes the viewing transformation complex. Here is a simple code which expresses that. First, we compute the viewport transformation, then we are computing the perspective transformation and then the camera transformation. We multiply them together, and so that the rightmost is the camera, because this one will be applied first to the world coordinates of our points, then the perspective transformation matrix, and then the viewport transformation matrix. And then for our points, which are defining as some lines in the space, and these lines are defining as some higher level primitives such as triangles or other polygons, which are defining as some objects, will be then multiplied with this matrix M, post multiplied as a column vector. And by that we will get the new points after this viewing transformation, P and Q. And if we want to then simply project them on the space, the final thing which we need to do is to divide each coordinate by the last coordinate, the W, so that we have this perspective division applied. So this division is actually realized at the very end of the pipeline, not when the perspective projection is applied, but we are carrying on a non-one equal last component of this homogeneous coordinate until the very end of the computation, after we apply the viewport transformation. And then finally, before we are drawing these points or the primitives which are corresponding to these points, we are dividing the coordinates with the last coordinate value. It might be interesting to know inverse transformations, and the inverse transformations for the other matrices can be relatively easy to compute because they are realized as a set of two transformations, like a translation and scaling, and we can easily find inverse of them and multiply them in the reverse order. And this is relatively simple to calculate. For the perspective projection matrix, the situation is also we can also find the inverse transformation to it. However, this transformation will, this matrix will be consisting of a lot of computations which are perhaps unnecessary. Therefore, we can multiply this inverse transformation with a certain factor, like for example, with a factor, with scaling factor f, and the scaling factor f will then, no, with the scaling factor fn, sorry, and this scaling factor fn will simply change the multiply each non-zero values in this matrix, and will change this matrix a little bit so that it becomes much more simple. So we will have the f values in the diagonal, and here the fn divided times minus 1 divided by fn will be minus 1, and then in the denominator we have again an fn, and this one will be also then removed and resulting in an equation which is, or in a matrix which is much more simple. Such an inverse transformation we, for example, need for picking of objects. So imagine that I want to pick an object in my screen coordinates, and I would like to know which objects did I pick in the world coordinates, so that I can sort of realize this picking and know which object I was interacting with. Therefore, I would need to perform inverse transformation of the entire viewing transformation, and in case of perspective projection, I would need such a perspective projection matrix P inverse, and instead of the more complex one, I could use a more simple one instead. It is important to note several important properties of perspective projection and sort of show their formal behavior. And one of such property is that the perspective projection transformation keeps lines to be lines after the transformation, and planes to be planes. So lines will be straight, and so will be the planes. So let's have a look at what happens to to a line under such a perspective projection. So here we will have a description of a line where we have one point, another point, and a vector between these 2 points parameterized with the parameter t. And then we are applying our transformation. The result of the transformation can be seen here. There is a multiplication with the transformation matrix M, which changes the positions of all our points. And it can be just considered as some new points R and R, capital R and small r, which obviously will again lead to some line. Now, after we perform the this operation of homogenizing the 3D line segment, meaning that we are performing the division with the factors which have been calculated in the z coordinate, sorry, w coordinate in the column vectors, we will end up with a description which is shown by this fraction. Here we can see that we can break down this this expression into again some position defined by the coordinate r, scaled by some scalar, and the same holds for the capital R and for the r. So we are still maintaining the um, the, the description of a line. However, instead of a t, we will have here some kind of a function of t, ft, which is a rational function. Our t appears both in the nominator as well as in the denominator. It turns out that this function is still, however, preserving the order, and that the vertices of triangles are mapped to other triangles under this transformation, even if the parameter t now doesn't go from linearly by changing it, but it is subject of modulation by this function. One typical example scenario we will be dealing with is a camera setting which have a symmetric view volume. This means that from the center of the camera, we will have the same distance to the left as to the right, and to the same distance as to the bottom as to the top. So it will be symmetric, and on the top of that, the pixel area associated with some pixel center will be a square. So the pixel size, pixel dimension in each direction will be the same. This will mean that if we have some resolution but defined by the values nx and ny, we have to have the same ratio between these two resolutions in each dimension as will be the lengths of right distance and the top distance. So this is another sort of constraint coming from the fact that the pixels will be squared after the as a property of this camera. A degree of freedom which will be remaining, which will be how far will be the sort of the near plane, or in other words, what will be the angle between the let's say the top distance and the um, the distance of the field of view, which we have defined here as theta. So, for example, in some cases, we will have this theta angle defining our field of view, and the unknown will be, for example, the t. So we can easily calculate the t, which would be necessary given if we will have the n and the theta. So for such a camera description, we can, based on the constraints of this nicely defined camera, we can calculate the other parameters easily. And with this, I would like to finish the viewing lecture. And now we have a complete machinery in order to make our objects interactively moving within the scene, as well as the camera. Please note that these viewing transformations are only partially applicable to the ray tracing, and we will be discussing some methods in the advanced ray tracing chapter or lecture, which will be related to the ray tracing or transformation of camera transformation of objects, object transformations which are defined analytically for the ray tracing purpose. So this is all for today. Thank you very much.